Hello students, welcome to mathematics class. So by the previous class we have concluded the unit 3, that is differential equation 3. So now from this class let us start the next unit, that is unit 5, and title of the unit is differential equations 4, and the content of this unit is homogeneous linear differential equations of nth order, equations reducible to homogeneous linear form, and higher order exact differential equation. So already in the third semester we have discussed linear equations and also homogeneous equations. So homogeneous means if you replace x by lambda x and y by lambda y, then after the simplifying the equation, the resulting equation must be same as the given equation. So then that equation is called as homogeneous equation. And the linear equation means that is of the form dy by dx plus py is equal to q, where p and q are the functions of x, right? So that is the standard form of linear differential equation. But here we need to consider homogeneous linear differential equation of nth order. So in the previous semester we have discussed only homogeneous linear differential equations of first order and first degree, but now we will going to start homogeneous differential equations of nth order. So their degree must be is equal to 1, then only it is called as homogeneous linear differential equation. Linear means the degree of the differential equation must be is equal to 1, and then equations reducible to homogeneous form. So that by making some substitutions we are going to reduce the non-homogeneous equations into homogeneous equations, and then higher order exact differential equations. So in the third semester we have discussed exact differential equations, that is the equation of the form m dx plus n dy is equal to 0. So that should be, or that is said to be, the homogeneous form if there exists a function u such that its derivative is equal to that equation m dx plus n dy is equal to 0, means du is equal to the differential of differentiation of the function u is equal to m dx plus n dy. So then that equation is called as exact equation. But here we are going to start higher order exact equations. So in the previous semester we have discussed only first order exact differential equations, but now we are going to start higher order exact differential equations. So these are the three main contents of this differential equation 4. So it is similar to the previous unit differential equation 3. So here also we are going to find complementary function and particular integral depending on the function on the RHS of the given differential equation. But one extra work is, first we need to reduce that homogeneous linear differential equation to homogeneous equations with constant coefficients, means whatever we have studied in the previous unit, the same is continuing in this also, but we are making some substitutions to reduce homogeneous equations to homogeneous linear equations with constant coefficients, whatever we have studied in the previous unit. So now let us discuss about the definition of the homogeneous linear equations of nth order. So here this is the definition of that homogeneous linear equation of nth order. So here a naught x power n into d power n y by dx power n plus a1 x power n minus 1 d power n minus 1 y by dx power n minus 1, and so on, a n minus 1 into x dy by dx plus a n y is equal to x. So in this equation a naught, a1, a n, they are all constants and capital X is a function of x. Then this equation is called as homogeneous linear equation of nth order. So in the previous unit we have discussed linear equation with constant coefficients, right? So for that and this equation there is only one difference. So here function x is there, but there it is a naught d power ny by dx power n and a1 d power n minus 1 y by dx power n and so on, an is equal to x, right? But here it is x power n. So that's why it is called as homogeneous linear equation. Means if you replace x by lambda x, then it doesn't make any difference. So that is the main point of that homogeneous linear equation of nth order. So here capital X, that is a function of small x. So to solve this homogeneous linear equation, first we need to reduce this equation to linear equation with constant coefficients, means that is of the form f of d into y is equal to 0, right? So f of d means any function or any equation in d. So for that we need to write the auxiliary equation, then finding the roots of that equation, then writing the corresponding complementary function. That will be the complete solution if RHS is 0. If other than 0, if it is any function of x, then we need to find the particular integral. So for finding the particular integral, already we have 5 cases, right? In case 1 e power ax, sin ax or cos ax, and x power m, e power ax into v, and x into v, right? So 5 types of particular integrals we have studied in the previous unit. So by using the previous knowledge, we are going to start, or we are going to solve the homogeneous linear equations of nth order. And now let us discuss method of solution of a homogeneous linear equation. So means how to solve the linear equation, that homogeneous linear equation. So by reducing that to linear equation with constant coefficients. So here the given homogeneous linear equation is, so let us consider the equation what we have discussed in the definition is equal to x, that is called as equation 1. So now to solve this homogeneous equation, we are using one substitution. So that substitution is fixed for each and every differential equation of this unit. So here to solve any equation, so first we need to put x equal to e power z. So here e power z, x equal to e power z, or we can write z equal to log x by using the definition of logarithm. Then it implies that dz by dx is equal to 1 by x. By differentiating this one, we will get dz by dx equal to 1 by x. Then we can write dy by dx. So here we have substituted x is equal to e power z, means x is a function of z, right? But here we need to, and y is a function of x. So we need dy by dx, means first we need to differentiate y with respect to z, then with z with respect to x. So this is the total derivative dy by dx, where y is a function of x and x is a function of z. So therefore here dy by dz into dz by dx. So already we know that dz by dx equal to 1 by x. Hence this becomes dy by dz into 1 by x. So now it implies that dy by dx equal to 1 by x into dy by dz. So on cross multiplying, we can write x into dy by dx equal to dy by dz. So by cross multiplying this one, we get dx into dy by dx equal to dy by dz, and consider this as equation 2. Now let us consider second order derivative of y, that is d square y by dx square. So here already we have dy by dx, which is equal to 1 by x into dy by dz. Then the same function must be differentiated once more to get d square y by dx square. So in dy by dx we have two functions, one is 1 by x and one is dy by dz. So let us differentiate that one. So first function 1 by x as it is, then differentiation of dy by dz is d square y divided by dz square into, again z must be differentiated with respect to x, that is dz by dx, then plus second function as it is, that is dy by dz, then differentiation of 1 by x is minus 1 by x square, then here it is equal to, this is 1 by x and we know that dz by dx is also 1 by x, then 1 by x into 1 by x becomes 1 by x square d square y by dz square minus 1 by x square into dy by dz, right. Now here the common term is 1 by x square and remaining d square y by dz square minus dy by dz. This is equal to what? And then this is d square y by dx square. Then on cross multiplying we can write x square into d square y by dx square is equal to d square y by dz square minus dy by dz, and consider this as equation number 3. And next, now put x into d by dx is equal to d by dz, which is equal to capital D. So here this is the operator capital D. So in the previous unit we have considered d as only d by dx, right, but here each differential coefficient is multiplied by x, right. So therefore x into d by dx is the operator capital D. So here it is there. So in this equation this d by dx is multiplied by x, then here d by dx is multiplied by x. So order of d and order of x are same, right, but each differential coefficient is multiplied by x. So therefore we have considered that operator as x into d by dx, and that is nothing but d by dz. And then here from equation 2, so what is equation 2? Here x into dy by dx equal to dy by dz. So already we know that x into d by dx is capital D, then this becomes dy, because we are not considering y in the operator. So operator is only x into d by dx. So therefore dy is equal to dy by dz, that becomes, sorry, this is equal to x into dy by dx. So means x into dy by dx can be considered as capital D into y. And from third equation, so here this is the equation 3. From equation 3, x square into d square y by dx square, right. So here d square y by dz square, that is nothing but capital D square, right, because d by dz equal to capital T, then d square by dz square equal to capital D square. So therefore it is d square y minus dy, because d by dz, that is capital D. So then simplifying this one, x square d square y by dx square is equal to, we can write this as d square minus d into y. d square minus d into y, because we have written that y in common. Then by taking d common, d into d minus 1 into y. So means second order derivative, that x square into d square y by dx square, that is equal to d into d minus 1. Then similarly we can write the next derivative, that is x cube d cube y by dx cube, that is d minus 1 d minus 2 y. So if the power of d is 3, then here we have 3 terms, d minus 1 d minus 2, not d minus 3, means the value of, or sorry, the power of d. If the power of d is 3, then the last factor will be d minus 2. Then if the power of d is n, then that will be d minus of n minus 1, 1 less than the power of d. So therefore here, continuing like this, we can write x power n d power n y by dx power n, which is equal to d minus 1 d minus 2 and so on, d minus of n minus 1 into y, right. So here x power n d power n y by dx power n, that is d minus 1 d minus 2 and so on, d minus of n minus 1 into y. So that is the expression for nth order derivative. Now from equation 1, so here this is the first equation, that is a naught x power n d power n y by dx power n, this a1 and so on, an minus 1 x into dy by dx plus an y equal to x. So here the previous term of this one is an minus 2 into x square into d square y by dx square, right. So now here, so we got d power n y by dx power n and d power n minus 1 by dx power n minus 1 and x d square y by dx square dy by dx in terms of capital D, and capital X is a function of x, and we have substituted that x equal to e power z. Then the first equation becomes a naught as it is, right, then x naught into d power n y by dx power n. Here we have the result for that, x power n into d power n y by dx power n equal to d minus 1 d minus 2 and so on, d minus of n minus 1 into y. So therefore let us substitute this one here. Then we got a naught as it is, because we have not considered the constant term in the simplification, that a naught d into d power n d into d minus 1 d minus 2 so on, d minus of n minus 1 plus a1. So here the next term is x power n into d power n minus 1 y by dx power n minus 1. So here we have n minus 1, sorry, n factors from d to n minus 1. So means d minus 0, d minus 1 and so on, d minus of n minus 1. There are n factors, and the next term will contain n minus 1 factors, because the power of d is n minus 1. So number of factors will be equal to power of d, or order of the derivative. So here order of the derivative is n minus 1. So therefore here d minus 0, d minus 1, d minus 2 and so on, d minus of n minus 2. So one factor less than the previous one and so on. Here I told that the previous term of this one, that is an minus 2 into x square d square y by dx square, that is nothing but d square y by dx square into x square is d into d minus 1 and an minus 2 plus here an minus 1 into capital D an, and we have written that y common for all the terms is equal to f of e power z, because here capital X equal to f of x and we have substituted x equal to e power z. So therefore that becomes f of e power z. So here that we have considered, where x is capital F of x. Now this is a linear equation with constant coefficients. Now this equation becomes the equation which we have already solved in the previous unit, right? So this equation is similar to the same equation whatever we have solved in the previous unit. Then that can be solved easily because already we have completed that unit. So here, and it is solvable for y in terms of z, because here the equation is f of d. F of d means the equation which is in terms of d into y is equal to the function is in terms of z, means the solution will come in terms of z only. Now if y is equal to capital F of z is its solution, let us assume that that as the solution, then putting z equal to log x we get the required solution, because our differential equation is given in terms of x and y, and our solution must also contain those two variables only. That z is a new variable because we have substituted that. So therefore our answer must be a function of x and y. So therefore we need to substitute z equal to log x and we get the required solution, that is y equal to f of log x. Instead of z we need to substitute log x. So therefore this is the procedure how to reduce the homogeneous linear differential equation into linear differential equation with constant coefficients, right? Now here we have a note how to, means this is the short note of all this procedure. So put x equal to e power z, that is the first point. Then x into d by dx, that is nothing but d by dz, that is equal to what? Capital D. Then x square d square by dx square, that is d into d minus 1. X cube d cube by dx cube, that is d into d minus 1 into d minus 2. If it contains x power 4 d power 4 by dx power 4, then that becomes d minus 1 d minus 2 d minus 3. Number of factors must be same as order of the derivative. So if it is of first order, then that is d only, second order d, then 1 less d minus 1. Then if it is 3, then d minus 1 d minus 2. Then if the order of derivative is 4, then d minus 1 d minus 2 d minus 3. So after substituting all these things, the equation becomes f of d. F of d is nothing but from a0 to an, that is the function of d. F of d into y equal to a function of z, and solve this equation. Then finally substitute z equal to log x or e power z equal to x, both are same, z equal to log x or e power z equal to x. So this will give the required complete solution. So here if f of d into y is equal to 0, then the complementary function itself will give the complete solution. If it is other than 0, then we need to proceed further to find the particular integral. So let us discuss some examples on this one, then you will understand easily. The first example is x square d square by dx square plus x into dy by dx minus 9y is equal to 0. So here this is the homogeneous linear differential equation. So that can be identified easily, that is if the differential coefficient is multiplied by the term x. If it is not multiplied, then that is the linear differential equation with constant coefficients. That is the only difference between those two. So here if x is not multiplied, then that is the question from the third unit. If x is multiplied, then we will come to the fourth unit. That is the only difference in identifying homogeneous linear differential equation and linear differential equation with constant coefficients. So here, to solve this one, we need to put x equal to e power z. So already we came to know what is the procedure of solving the equation. So first of all, put x equal to e power z, or it implies that z is equal to log x, right. Then d by dz equal to x into d by dx, which is equal to capital D, right. Or simply you can consider x into d by dx equal to capital D, and x square into d by dx square equal to d into d minus 1. So these are the substitutions, because we have only x square into d square by dx square and x into dy by dx. So therefore consider these two only, d and d minus 1. So now consider this as equation number 1. So by substituting all these three, equation 1 becomes, now equation 1 becomes here x square d square y by dx square is equal to what? D into d minus 1 into y plus x into d by dx is capital D, y as it is minus 9y is equal to 0. Now it looks like the linear differential equation with the constant coefficients. Then here we can write that y common. So for that, d into d minus 1 plus d minus 9 into y is equal to 0. Then simplify this one, here multiplying d square minus d plus d minus 9 into y is equal to 0. Now d and d get cancelled, it is d square minus 9 into y equal to 0. Then auxiliary equation is what? M square minus 9 equal to 0. It implies that m equal to plus or minus 3. So once you get the roots, you will already know how to write the complementary function. So if the question is in the previous unit, we will write the complementary function as c1 e power 3x plus c2 e power minus 3x. But here we cannot write like that, because here we have substituted x equal to e power z. So therefore here y equal to c1 e power 3z. Instead of x we need to consider z, plus c2 e power minus 3z, and this can be written as the c1 as it is, e power 3z can be written as e power z whole cube, right, plus c2 e power z whole power minus 3. Then what is e power z? X, right. So therefore it is c1 x cube plus c2 x power minus 3 is equal to y, which is the required solution for the given differential equation. So here be careful while writing the complementary function, because if you write here c1 e power 3x, then your answer will be wrong, because we have substituted x equal to e power z, then only we are able to put x square into d by dx square equal to d into d minus 1 and x into d by dx equal to capital D. So means we have substituted function of x as a function of z, means first we will get the solution in terms of z, then we need to replace that function of z by x, that e power z equal to x. So if it is only z, then put z equal to log x. So therefore here this is the required solution for the given differential equation.